when wearing this contraption, I feel a little bit like Madonna, but hell, she might be out of my league. It was a joke. Right, so I'm going to be talking about some things that I understand and a lot of things that I don't understand. And so the less generous amongst you might say, well, hell, every time he stands up, he doesn't know what he's talking about. But this is really a call to action around a particular system that I think we need to really understand a lot better. But before we get to that particular system, I'm going to talk you through some of the systems that I think we do understand a little bit better. So I changed the title, Beneath the Waterline. And beneath the waterline, because what I'll be talking about is dynamical symmetries and clustering. And clustering appears in all sorts of different contexts. And for this thing to work, all sorts of contexts, not least of which, if you look beneath the waterline, there are a set of clusters called water clusters, which have a rather transient existence. They are bound together by, of course, hydrogen bonds and van der Waals interactions. They have a transient existence. They appear, form, live for a short time, and then dissolve again and reform clusters. You might wonder, how on earth do we know that water clusters exist? How do we see them? That question also hangs over nuclear physics as well. So what's shown here is the Ocado diagram, and I've taken our water line and translated it onto this diagram here. The Ocado diagram, for those of you who haven't seen it before, is a way of showing where cluster structures might exist in light nuclei. There's a whole range of light nuclear systems here, and typically clustering is a manifestation which appears above the alpha decay threshold. And so if you want to see 3 alpha particles, take the case of carbon-12, usually you would have to put in 7.3 MeV of energy to get to that cluster structure. But if we take the calculations, for example, wherever Thomas is, I saw him a minute ago, that he showed yesterday from his FMD calculations, or here some calculations from anti-symmetrized molecular dynamics. In these calculations, the clustering isn't put in explicitly. This is a 12-body wave function, and the clustering emerges naturally. The excited state, laser pointer is rubbish. The excited state, the Hoyle state, is this well-developed cluster structure here. But if one looks at the other diagram, the lower energy one, which says 0, 1 plus, that is the structure of the ground state. And actually what you see is a triangular symmetry. It's almost like you've taken those alpha particles and squeezed them and squashed them on top of each other, but nevertheless you have that threefold symmetry. So a dynamical symmetry, if you like. And the question then is, how do you see what's going on below the alpha decay threshold, or if you like, the analog being below the waterline? Now, I'm going to take you back in a time machine back to 80 years ago, 1938, piece of work done by Hafstad and Teller, which really told the future of the subject. So Hafstad and Teller, based on, I remember Teller had a background in atomic physics, so based on that background, applied that understanding to nuclear physics. And here was a prediction of the structure of a whole sequence of light nuclei. And at that time, very little was known about these systems. So maybe the ground state energy and a few excited states, but nothing more. So this was a prediction 80 years ago, and we're still working to test whether this prediction was true or not. I'm going to focus in on a few of their predictions and try and understand how they were able to come up with this sequence of excited states for these light nuclei. So their conjecture was that in the ground states of light nuclei, they were dominated by alpha particle cluster structures. Okay, so that's the premise on which they built everything. In the case of beryllium-8, is there a laser that really works? This is one of these things got a laser pointer on it? Yeah, so the premise was that the ground states were built of alpha particles, and so if you look at beryllium-8, what they predicted was a structure which was 0G, and G in this case means Gerada, symmetric, and then there's a 2G, so 2 plus and 4 plus, and you can see they predicted a nice rotational J into J plus 1 structure for that. If one skips beryllium-9, which is interesting because they predicted the existence of nuclear molecules all the way back in 1938, but let's focus on carbon-12. Carbon-12, they took what they knew from atomic molecules, so here's a nice atomic molecule which has a nuclear application, which has a particular point symmetry, D3H. They took what they knew from atomic molecules and said, well, okay, based on that, we should get a spectrum for carbon-12 which looks like this. So we would get a 0 plus, 2 plus, 4 plus, and there should be a 3 minus, 4 minus, 5 minus, etc. Okay? And then, being bold, if we look at oxygen-16, so this now has a tetrahedral structure. Here's a tetrahedral molecule, and the point symmetry now is this group here. Now, based on this symmetry, you would get a 0 plus ground state, a 3 minus excitation, a 4 plus, and the interesting thing is this degenerate 6 plus, 6 minus. So there's a rather interesting signature there. So if one looks at the experimental situation, so what have we managed to do in that last 80 years? Well, we've understood beryllium-8. Here is the rotational spectrum, and here is the point symmetry for that particular structure. You see a 0 plus, 2 plus, and 4 plus. And the thing which is spinning away there is the Green's function Monte Carlo calculation, so an ab initio type calculation of the structure of beryllium-8. And that calculation was done about 15 years ago or so. And I think before those 15 years, there was a begrudging acceptance that cluster structure might have an important role in the ground state of nuclei. These calculations were really a transformation. Finally, through an ab initio type approach, you can see the clusters, and I think at that point people believed it. Now, in carbon-12, let's just try and unpick why Hastad and Teller understood that there might be a particular rotational spectrum. This is an equation cut out of their paper, which shows how you build those rotational states. There's two quantum numbers, there's J and K, K being the rotation around the symmetry axis. Okay, so the lowest K quantum number could be 0, and then all rotations around an axis which is aligned with that plane, and you can see, as is shown by this rotation here, as 0, 2, and 4. And this is just like a beryllium-8 rotating, so K has vanished here, and we see a rotational band just which looks like its analog in beryllium-8. The next possible excitation is when one gives each of the alpha particles 1 unit of angular momentum. We've got then K equals 3. You see that generates a spectrum which is 3 minus, 4 minus, and 5 minus. One could breathe life into these structures. So this is quite a compact arrangement of alpha particles in the ground state. They've been forced on top of each other. A monopole excitation. Those alpha particles would be further apart, and then one would generate a new set of states with, in Hastad's and Teller's picture, with identical symmetries, and you would get, for example, a 0, 2, and 4. And the interesting thing is that in this picture, one would get a close to degenerate 4 plus and 4 minus state. So that's an interesting signature to look out for. So if we go to the experimental situation, so again, what have we done since those 80 years? Well, we've managed to characterize the spectrum of carbon-12 really well. Here is the 0, 2, and 4 rotations associated with this configuration. Here is the 3 minus state. That's been known for a long time. 4 minus state, here in the data tables, it says 2 minus. This is really now, we know, a 4 minus state, so thanks to the work to the work of Hans's group. We also, as you heard in the talks yesterday, are beginning to characterize the rotations of the Hoyle state with a 2+ state and a tentative 4+ state. Now, if one really believes these dynamical symmetries, then one would ask the question, I should have mentioned that you see that there's this nice degeneracy experimentally of these 4+ and 4- states, but one would ask if this is really true, where is the 5- state? We did a piece of work on our own world-leading accelerator facility at the University of Birmingham. We have a cyclotron, and just to show that you can do good work on small-scale facilities. Actually, everything I'm talking about here was done on small-scale facilities. We managed to find the 5- state, and what we can do is we can sit in the reference frame of that decaying carbon-12 nucleus and map out where the alpha particles are going, measure the angular distributions, and here you can see the experimental data. If you look at it long enough, you'll see that it agrees with J = 5. So I think we, up to this point, have a reasonable understanding of the structure of carbon-12, and we could carry on looking for more states, and you say, well, okay, where are the other states in the rotational bands? Or you could say, well, okay, if you really understand dynamical symmetries, maybe you look at the next nucleus. So here, forgot this slide was here. Here is the summary of dynamical symmetries in carbon-12. So if we look at oxygen-16, which is the next system, and already you can begin to see what the challenge is. So the level density in oxygen-16 above the decay threshold is complex. So to really pin down what's going on here is going to be a bit of a challenge. Not only might we have tetrahedral type structures, but we're going to have other types of configurations, cluster configurations, which can play a role, not least of which is this most exotic one. Let's, before we despair, let's go back to look at what Hafstad and Teller predicted for us. So again, here is a cutout from their paper. What you see here is their prediction for not only which particular spin states you can get, but also the rotational spacing. You can see that the moment of inertia that characterizes this band is 4 times that. Well, it's actually twice that of beryllium-8. And if you think about rotating a tetrahedron, and you can possibly see it best at the bottom here, here you can see 2 beryllium-8s rotating, and hence why you've got this particular characteristic moment of inertia. Now, what we would like to do is see experimentally if we can see this pattern here. Now, before I take you to the experimental data, here's a more modern calculation, very similar to 2014 by Baker and Iakello. And you can see that this is very much, well, it's almost identical to the predictions of Hafstad and Teller, 0+, 3-, 4+, double degenerate, 6+, 6-. Slight complexity that if you have a monopole excitation, you can expand the dimensions of this tetrahedron, and you get a repeating pattern just like we had in carbon-12. On the other side, one sees the experimental situation. Actually, it's compelling, isn't it? You look here, well, of course, there's a 0+. There's a 3-, there's a 4+, and then to slightly higher, there's a 6+, but no 6-. Well, okay, we still need to find that. You can see that there's this analog of this band here. And so maybe oxygen-16 does have a tetrahedral structure. And here you can see from Baker and Iakello's paper, again, these 2 tetrahedrons arranged so into rotational structures, 0, 3, 4, 6, 0, 3, 4, 6. And one can compare, based on this model, electromagnetic transitions. So here you can see the theoretical transition of this state here, the 3- to the ground state. This is a theoretical prediction. This is experiment. Here is the calculated energy and experimental energies. The 4+ state, again, remarkable agreement. And finally, well, the transition hasn't, not surprisingly, been observed, but the energy is about right. So again, from the electromagnetic properties, this looks rather compelling. Now, this is not the first calculation that has been done of oxygen-16, and nor will it be the last, hopefully. I think there's a lot more work to be done here, but here's another take. Here's an alpha cluster model calculation, not from B squared FH, but BS squared. And here they see a whole series of alpha cluster type structures, so the tetrahedron, some planar structures, and a linear structure. And here you can see two density plots, which for the planar structures with two different types of interactions. And you can see that the cluster structures, you can see two alpha particles close together, too far away. Now, again, one can take these, the data motivated by the alpha cluster model and arrange them into rotational bands. So here's a tetrahedron, positive parity, negative parity, 0 plus, 3 minus, 4 plus, 6 plus. And then there's some bands here associated with what they call the kite configuration. And it's those bands that I want to come back to. Here you can see, again, the experimental data arranged associated with those cluster configurations. And I'm going to compare them with the algebraic cluster model of Vickers and Kello. The interesting thing is that if you take this particular 4 plus state, which is associated with this cluster rotational band, this in Vickers and Kello's calculations is part of this ground state rotation. And if you take the band head here of this cluster configuration, it is mapped into the band head of this rather extended tetrahedral structure. So which of these pictures is right? Maybe neither is right. Now, we can try and answer that question in lots of different ways. One of them being by doing alpha transfer. So here are some measurements done at Munich by the group from Birmingham, where we take a lithium-6 beam, transfer an alpha particle onto carbon-12. So lithium-6 beam in, transfer an alpha particle, deuteron whizzes around here, hits the focal plane, and we can tag the states in oxygen-16 by analyzing the focal plane. And then with some silicon detectors in the chamber, look at how the oxygen decays into carbon plus alpha. Yep. And then we can ask the question, how many times did it decay to the ground state? How many times did it decay to the excited state in carbon-12? So here is, this is type of approach has been taken for characterizing all of these states in these cluster bands. So this is the ones, these two, the bands that I'm talking about are associated with the kite configuration. Here you can see the total spectrum in the focal plane. Here's tagging on the ground state. Here's the 2 plus state. And the particular state that we were interested in is this 5 minus member of that rotational band, and you see it decays exclusively to the ground state. And you maybe at the back you can't make this out, but what this shows here is that all the states in the rotational bands in the cluster model, identified in the cluster model, decay in exactly the same way. They decay to the ground state of carbon-12. So they all have exactly the same character. And so then one would say that these states then have a structure which is more like this rather than a tetrahedral structure. Or even perhaps one can describe these states as an alpha particle rotating down around a carbon nucleus given the way they decay. So do we see a fingerprint of tetrahedral structure in oxygen-16? Well, not yet, but nor would I say that we fully understand what's going on in oxygen-16. In the last few minutes that I've got, what I want to do is go to slightly higher energies and go back to a story which isn't 80 years old, it's 50 years old, which is the existence of the 4 alpha particle chain structure in oxygen-16. This is some work which was done by Chevalier et al. So they used a very simple reaction, alpha plus carbon-12, looked for a final state of 2 beryllium-8s. And since beryllium-8, as we know now, has 2 alpha particle structure, if you've got a final state which is beryllium-8 and beryllium-8, well, maybe you've populated something which has got a linear arrangement of 4 alpha particles. And that was the assumption at the time. They measured this rather wonderful excitation function, managed to measure some of the angular momenta associated with these. And if you plot them, you see a linear arrangement. Well, you see a rotational band which has a moment of inertia which is associated with a linear arrangement of the alpha particles. Now, a good test of whether you understand that is to say, well, okay, if there's a 2, 4, and a 6, there must be an 8. And some later work went off to look for that 8+ state and failed to find it. So the question of the existence of the 4 alpha particle structure in oxygen-16 has been around for those 50 or so years. So here's some work that we did at Notre Dame, another, forgive me, small-scale facility, slightly bigger than Birmingham. But the fantastic thing here is that you can study, so we studied this reaction. Again, this was the reaction studied by Chevalier, but in fantastic detail. So here you can see the excitation function. There are 400 data points here, which means that we had to change the energy on the tandem 400 times. So astonishing. You just couldn't do that. Imagine going along to Ganil and saying, like, I want to do an excitation function of 400 energies. They'd say, well, okay, you might be mad. All right, so the other thing that we were able to do is to look for the decay of these states into the Hoyle state. So this is rather extended 3 alpha particle state in carbon-12, and you can see that the resonances map across. I'm nearly done. What this shows is just a compilation. We also measure the decay to the triangular configuration in carbon-12, so the 3- state. We were able to measure for each of those 400 data points complete angular distributions, and we can fit those angular distributions with a functional form which looks like this, which tells us the amplitude of each angular momentum, the phase, and here's a Legendre polynomial, and here you can see some fits. And that allows us to do a phase shift analysis across that complete energy spectrum. And so here's the original excitation energy spectrum. Here's where the spin 2, 4, and 6 would be for the change state. You can see here's the amplitude of the 0, 2, over here 4, 6, and then there's the phases associated with each of those angular momenta. And if we take our data and truly try and understand what's going on where there's J equals 2 identified before, actually you can see most of the action, the sharp structure is over in the L equals 4 partial wave, where the L equals 6 member of the band was, well, that looks to be split between 2 and 4, and the spin 6 structures don't kick in until much higher energies. So where does that leave the chain configuration in oxygen-16? Well, I think the summary is something like this. I think we no longer believe that the chain structure exists. Nevertheless, this is a really rich and complex series of resonances which decay into rather exotic decay channels. So they decay preferentially to 2 beryllium-8s. They decay preferentially into the Hoyle state, a very exotic state. What is the nature of these resonances? You will know that one has to do a proper analysis. So at the moment, I've got a poor student whose job is to do an R-matrix analysis of this whole spectrum, and that may be the death of him. We'll see. If he survives that process, then we will hopefully in a year or so time be able to tell you what the nature of these resonances are. So here's my summary. I think we have a good understanding of the symmetries of carbon-12, and these seem to obey some dynamical symmetries, D3H symmetry. And the question for us is really, can we, if that's right, can we take that understanding and take it to a different system, oxygen-16, and see those dynamical symmetries? And there's a lot of work to be done, and as I said at the beginning, this is really a call to action. I think this is a key nucleus now in trying to understand what's going on in light nuclear systems, both from a theoretical and experimental point of view. The one hint or hope is that, yes, if you've got a dynamical symmetry, there should be a 3- state. Our challenge is to understand the rest of this. Thank you very much.
Okay, we have a couple of minutes for some quick questions.
When you analyze the energy, excitation energy using the form of I plus times I plus 1 combination. So in this case, actually you assume the collective rotation of the cluster states. So it is really happen, or do you have other signal to identify the mechanism of such excitations?
Yeah, so if your point is that, yes, if you just look at energies alone, you can fool yourself. So how can you characterize the nature of these states? So in the case of carbon-12, so once they become above the decay threshold, one can look at alpha decay widths and things like that and compare them to something like the Wigner limit, and that's a good test of the development of the cluster structure. Another way of characterizing these states is electromagnetic transitions. Okay, for bound states, that's fine. For unbound states, measuring electromagnetic transitions is a real challenge, but I think that's really the next step from an experimental perspective. Can we really measure electromagnetic transitions for alpha unbound states? So at Birmingham, on our world-leading facility, we're developing a setup to measure the BE2s of alpha unbound states.
Yeah, Martin, it's a little bit related to the previous question. It happens that I think most of the cases of this picture of rotating cluster, that this I plus 1 behavior is not fully fulfilled. And most of them you have deviation when you expect that this is the most rigid structure that really can mimic rotation. So what's the explanation of deviation of some points?
Well, okay, there's lots of potential explanations. So the fact that I draw a picture here which shows 3 alpha particles and they're all in a nice compact arrangement and nothing changes as you spin the system, that's not true. All you have to do is look at the calculations at AMD or FMD. You will see that the alpha particles are not exactly in the same coordinates as you rotate the system. They're still clustered. So the same underlying symmetry is there, but it's nuclear physics. Nothing is perfect. We're looking for the first order, 0th order understanding.
When you go to heavier system, is there any evidence that this type of alpha clustering disappears or weakens?
Yeah. So certainly if you were to get beyond the SD shell, so best cases are when you're in really, really light nuclei. Polonium-212 might be a good example where you've got an alpha particle outside a closed shell. Right at the end of the N equals Z line, we know you get enhanced alpha decays. The correlations are really important in building up the alpha particle structure. So ideally, what you need is neutrons and protons to be in exactly the same orbits. Okay, and that, as you go to heavier nuclei, of course, that's no longer true.
Well, thank you. Okay, thanks again.